Okay, we're now live on YouTube, so Mark, take it away.
Okay, very good. So I want to speak today on my thoughts about securing EcmaScript. This is something that I've been working on for a very long time now, starting with the Kaha project and my contributions to the design of EcmaScript 5. And from interacting with Bradley, I've come to understand a lot of the relevance of what I've said for a lot of the issues facing Node right now. So this is the overview of the talk. I'm going to start by explaining the focus problem that I want to orient this talk around. And I want to stress that there are many security problems, and different security problems will call for different mechanisms. And altogether, I very much believe in defense in depth, that we have to fight on all fronts. Security is hard. And when there is a well-motivated problem, then we should figure out what we need to do for that problem. And if we can build mechanisms that solve other problems as well, great. So I'm going to focus on least authority libraries as the motivating problem. Then I'm going to explain why JavaScript is especially well shaped for success at the kind of security I've been trying to bring to JavaScript. I'm then going to talk about the main mechanism that we've been working on and that I'm proposing as the right mechanism to address this problem. And then I'm going to return to the problem and explain how these mechanisms brought together actually do address the issue. So start with the problem, least authority for libraries. There are a variety of vulnerabilities that we've seen that come from the fact that people build applications and websites. It happens on both the browser and server, and on mixed browsers and servers like Electron, from the fact that anytime you build something, you probably link in lots of code, lots of library code from third parties that you don't vet. And often that code comes along with other code, and sometimes that code misbehaves. So there's been some significant concern about Electron to the point that Brendan reports that Windows 10 Store was considering banning all Electron-based apps, including Slack and Signal. So that's quite a severe reaction, indicating that the problem is quite severe. And the problem is driven by the fact that in our current systems, when a bunch of code is loaded and linked together, it's all completely vulnerable to each other, that every bit of that code runs with all of the authority of the application, or on the server side of its user, and on the browser side of all the authority given to the web page as a whole. And Brendan refers here to POLA, which is the principle of least authority, which is the most important first principle to turn to at all granularities, including the library granularity that I'm focusing on today. And that principle is the principle that one should give a component, again, a component at any granularity, one should give a component only the least authority that that component needs to do its legitimate job. And then that component still might misbehave, but the limit on the damage that it can do if it misbehaves is limited by the authority that's been placed at risk through its misbehavior. There's also the Princeton No Boundary series that documents rather massive. They're looking at browser properties, but what they're identifying as a form of vulnerability applies equally to server-side apps and to mixed browsers and servers. What they're documenting is that people link in third-party scripts all the time without understanding the vulnerability they're creating. For example, Walgreens, by virtue of third-party scripts it was using on its website, patient prescription information was being leaked to those third-party scripts and the websites from which the third-party scripts came in clearly blatant violation of HIPAA. Likewise, in Princeton's own information security course, they found that they were linking in libraries that caused exfiltration of grading assignments, student names, emails, grades, and instructor comments to the source of those third-party scripts. And that's in violation of something called FERPA. So this is a pervasive problem. Sometimes you will hear the security perspective that, well, any code you link into your website or link into your server, any library that you've decided to load, is you will often hear the phrase trusted code. And the implication is that you should only use third-party libraries that you've fully vetted, that you're completely certain is secure, or that you're willing to risk all of your users' security on. And this is rather ridiculous advice. The purpose of this advice, I think, will only be understood as advice whose purpose is to shed liability rather than to protect users. It's very much like when the car industry was saying things like, oh, your Pinto blew up. Well, it's your fault because you had a collision. You shouldn't have had a collision. It was operator error. We need to understand what realistic behavior is for use of the programming language. Cars became more forgiving of realistic behavior over time. It doesn't mean people don't crash. It doesn't mean people don't get hurt. But they became more forgiving of realistic behavior. It was much easier to drive a car safely, and it was much easier to survive many accidents. And our industry needs to make that change as well. We should take responsibility more responsibility for the realistic behavior that our programmers engage in and what's necessary to help them help their users be safe. Much of computer science and much of software engineering can be seen as being about this trade-off curve between safety and usefulness. When we compose components, in order for them to cooperate, in order to gain the benefits of cooperation, they might instead interfere with each other destructively. And if we if we're too enthusiastic about separating things, like Java applets with that security model, we can just create uselessness. So when we talk about destructive interference, when the destructive interference of concern is accidental, we call those bugs, and that's the domain of software engineering. And much of computer science has been concerned with that, how to gain the benefits of cooperative composition while limiting the damage from accidental interference. And when the interference is intentional, we call those attacks, and those are studied by computer security. But my message and my work is all premised on the idea that I don't much care whether the interference is accidental or intentional. The mechanisms that we've built to cope well with accidental interference are very similar to the mechanisms that are effective against purposeful interference, against attack. And if you engineer trying to be safe against attack, you're also much more likely to be safe against accidental interference. And we see these in the security, in the architectures, not the security architectures, the software engineering architectures of systems that are built that are very, very highly reliable. It's often using mechanisms that are in fact quite similar to mechanisms you find in good security architectures. And the progress of computer science, both software engineering and security, can be seen as the progress of the discovery of modularity and abstraction mechanisms lifting the trade-off curve. So in JavaScript, it's started off, when I first got involved, it was the days of EcmaScript 3. And Doug Crockford convinced me that JavaScript was actually already set up well to be a starting point for success on this quest. And the reason was a historical accident. Conway's law is the law that organizations can only build engineering artifacts whose communication structure mirrors the communication structure of the organization. Well, JavaScript started as a language only for scripting web browsers, but it was split between two standards organizations, ECMA, which had responsibility for the language, and W3C, which had responsibility for the host API, the API for interacting with web pages and communicating on the net, etc. And the result was that JavaScript has an almost perfect division that's analogous to the division that we see in hardware between user mode instructions and system mode instructions, or the distinction we see in operating systems that builds on that distinction between user mode instructions and system calls. The JavaScript language is almost purely a language for internal computation, except that it provides one means for a host, like a browser or a server, to make it possible for JavaScript programs to interact with the world outside of itself, which is to look up host objects in the global scope, look up objects bound to names that are outside the names standardized by the JavaScript standard in the browser, like document and window and XHR, on the node, all of the node APIs, that all access to the external world starts with that global scope lookup. And therefore, if you can intervene in that global scope lookup, you can virtualize all access to the equivalent of system mode, and you can do the equivalent of building virtual machine monitors and operating systems. Furthermore, the JavaScript primordials, which are the objects that exist before code starts running, have essentially no hidden state, meaning that all of their mutability, all of their abilities to enable internal side effects are all in properties. So if you freeze all of those properties, there's no mutability left. So this deals with the external mutability of and external effects via the global scope, and the internal mutability by corruption by shared access to the primordial state of the objects that the primordial objects of a realm.
Wait,
I'm sorry, go ahead.
I guess there's a lot of words that are not necessarily super clear to me, but
Okay.
are you, like, when you're saying primordial, are you saying that any like object that may be backed by a C++ object? Because then freezing won't do anything, right?
What I'm saying is the primordial object standardized by JavaScript as opposed to the host.
Right, but I guess like is that actually interesting? Because like all the damage you can do is by calling into C++ land, right?
Right.
However,
I'm making use of both of these facts. The first one is the ability to intercept any attempt by JavaScript to access host objects so that you can virtualize the host. You can virtualize and deny by use of the intervention on global scope lookup. And so that's what I'm using for corruption, for dealing with corruption and attack via access to host objects. And then additionally, for among the JavaScript objects themselves that are co-loaded into the same realm, I'm going to make use of the fact that there's no hidden state beyond the properties among the primordials, so I can also protect that loaded code from each other. It's those two things brought together in combination which are powerful.
All right, thanks for clarifying.
You're welcome. And by the way, please continue to interrupt as things are unclear or for questions or comments. I do want to get through the presentation before extended discussions, but feel free to interrupt. And if I feel like a point is something I want to postpone, I'll just take responsibility for postponing it. Also, let me mention the two asterisks here. It's an almost perfect separation. Among the JavaScript primordials today, there are two exceptions to this. One is access to the current time via date.now or the date constructor invoked with no arguments. And that's being able to read external effects from the outside world. It's still not an ability to communicate. And the other one is math.random, which doesn't have anything to do with external effects at all, but by virtue of being statically accessed in the primordials, if there's a bad random number generator, anything less than a cryptographically strong random number generator, that creates a communications channel between object subgraphs that should have not been able to communicate. So those are both minor exceptions, but those are both exceptions we can deal with. I'm not going to come back to that in this talk unless there are questions. But other than those two exceptions, I don't know of any significant way in which JavaScript fails to uphold the separation of computation versus effects. So starting with the design of EcmaScript 5, when I got involved, it was at that point the EcmaScript 3.1 revolt against ES4, which then became ES5. But starting with ES5, we have been consistently shaping EcmaScript going forward to be able to support the kind of security I'm explaining today, to support object capability security, both at coarse grain and at fine grain. And a lot of the elements that we've gotten into EcmaScript to support our security goals, we got into it by arguing for them largely on the basis of modularity goals. Once again, corroborating our premise that security is just the extreme form of modularity, and to a large extent, the same mechanisms help with both. So for example, proxies and weak maps were put in there with the motivating use case being membranes. A membrane is an abstraction built out of proxies and weak maps in order to separate two subgraphs and to preserve the separation as the graphs grow dynamically. So over here, we've got a blue subgraph in the center surrounded by a membrane built out of proxies. The half circles are proxies. The ones pointing outward are internal proxies for objects on the outside. The yellow half circles pointing inside are external proxies for the ones for the objects inside. And the proxies emulate the objects that they're talking to, so that for most purposes, the programmer can reason as if the membrane isn't there. And the membranes were designed to support simultaneously these three goals: that they're transparent by default, that if the membrane isn't doing something to change behavior, it's as if it isn't there; that it forms an impenetrable boundary, that as new references cross the membrane, they're wrapped or unwrapped to preserve the boundary between the subgraphs, and that it supports purposeful distortions, which are the reason you introduce the membrane. If they're only transparent, then it might as well not have been there. So revoking access, creating subjective views, or policies that protect delicate internals. This is actually where the membrane metaphor came from, which is a cell membrane protects the delicate internals of a cell from the rather chaotic world outside the cell. And the Firefox internal security architecture is actually built out of exactly this. They started off with their own ad hoc membranes in C++ that were largely unprincipled. They've moved to still something that's a little bit special case from C++, but altogether is essentially the membrane architecture that corresponds to what we build at the user level with proxies and weak maps. And their whole interrealm security architecture supporting all the bizarreness of web security is built essentially only as membrane-induced distortions. So the main mechanism I want to focus on today is primordials, and in order to explain that, is realms. And in order to explain that, I want to introduce some distinctions first, definitions. So I mentioned primordials. The primordials, what I mean by primordials, are all of the objects standardized by EcmaScript, not by the host, that are mandated to exist before code starts running. By primordials, for reasons that have become clear, I'm going to exclude the global object. I'm just going to consider the global object as in a distinct category. And so the primordials is this graph of objects we're all familiar with. Among the primordials, there's a special category, which I'm going to call undeniables, which are the ones reachable by syntax, meaning that if before untrusted code starts running, an initialization code tries to monkey patch the primordials, to substitute things, to change the environment that later code finds itself to run in, as long as the later code is not translated, there are certain objects among the primordials that it can just reach by syntax. A object literal evaluates directly to an object that inherits from the original object.prototype. Function literal evaluates an object that inherits from the original function.prototype. And even if, no matter what we do to the namespace, the binding to those objects themselves are not something we can intervene on. The global object, of course, has properties that refer into this group of primordials and are essentially the routes for navigating among the primordials. And there's a special relationship between a certain set of primordials and the global object. Those particular primordials I'm going to call the evaluators. So the eval function and the function constructor both evaluate code where the properties of the global object are also at the end of the scope chain of the scope in which they evaluate code. So the dotted lines here are about what object is at the end of the scope chain of the code as evaluated by those evaluators. The other thing that is really rather amazingly fortuitous at enabling JavaScript to be a starting point for good modularity and security goals is that it's already the case on both the browser by virtue of same origin iframes and on Node by virtue of VM create context that we have multiple isolated realms. That when I say isolated, I'm referring only to the objects standardized by JavaScript, excluding the host objects. And when a new realm is created, it's essentially isolated from all of the other realm, except that the creator has an initial pointer into the realm they just created. And then all further connectivity and interaction has to be bootstrapped from that initial pointer. However, as anyone who's actually tried to make use of this particular feature for isolation for whatever purpose has found is that that as an isolation mechanism really conflicts with the usability of JavaScript through a phenomena that I call the identity discontinuity. And my own experience with that is the identity discontinuity, even for very knowledgeable experts who've hit it again and again, is when you try to do cross-realm programming, it keeps catching you. It's just a much harder problem than you can anticipate. So the identity discontinuity is, for example, that if Alice in one realm, in realm A, evaluates an array literal, it inherits from her array prototype. And then if through cross-realm interaction, Bob in realm B obtains a reference to that array and asks, is it instance of array? The answer will be no. And the thing that really makes this identity discontinuity so hazardous is not so much the instance of test, that's the obvious one. It's that when you then follow pointers starting from the object from the surprising realm, you find yourself traversing the primordials of the wrong realm. There's this cross-realm accidental leakage that just keeps happening. So we'd like to bring about useful isolation, but without making our users have to face this very difficult problem of the identity discontinuity.
Oh, Mark.
Yeah.
So, I mean, I agree, but I also think that there is a programming model where we don't need to do this, right? And the browser is exactly that case. With cross-origin, we can send messages and we don't need direct references, and that's a perfectly okay.
Right. So cross-origin is fine for the separation between pages. It is completely unrealistic for the issue of LinkedIn libraries. The 8,000 websites that the Princeton No Boundary series found were vulnerable to libraries that they linked in, that they're using as libraries, that use the opportunity of being linked in as just a component of a website to exfiltrate data.
Yeah.
Anybody who's tried to use code between, over post message between different origin frames in a browser knows that it's a very awkward interaction. You don't try to do that with your own libraries.
Wait, but like we can, right? Like there's work showing that you can do that. Right? It's like
if you're talking about the comlink work from Google, is that what you're referring to?
No. So Mickens' work, I think it's called like Pip. I can look it up. It's James Mickens, but basically, like we have ways of transforming libraries that are intertwined into extracting them to separate realms and doing message passing between them. And if they're not doing that, then they're doing like something that's very much intertwined and might not be isolated anyway, to the point where I'm not sure what you're actually getting.
Okay,
So,
so
can I interrupt for a second?
Yeah.
We were suddenly comparing the web's model to Node's model. We don't have this kind of multi-realm iframe situation in Node. People are just requiring other modules and loading them into the same realm. In very old versions of Node, we tried the multi-context approach, kind of what you're talking about, and there were problems with it. So I'd be curious on how you suggest we solve kind of the identity discontinuity that we saw way back when, that Mark also touched on, and also the problems of changing programming models entirely for these things.
yeah, but if there's work on trying to do this in the browser other than the comlink work, I'd certainly be interested in hearing about it. So please do send me the link. Let me ask, based on the comlink experience, let me ask what sort of the crucial question from that work, which is, does this, so to speak, transparent linking across a post message rely on async functions and doing an await at every cross origin interaction point?
So this is actually, it's called Polaris. I'm pretty sure that's what it is. They did solve that. You need to actually do a little bit of scheduling yourself, but it gives the appearance of synchronous function calls while still using the asynchronous post message. Oh no,
okay. So at this point, I'm going to postpone this question because I'm not familiar with the work. I'm very interested in the work. And if there's time at the end, I would like to come back to it because there's a particular weakness that I know from the comlink work that it still sounds from this like it might be vulnerable to, but obviously I don't know yet. With regard to more conventional use of post message without source transformation or anything that tries to mask these differences, it's incredibly awkward to try to compose code through post message, and nobody tries to do it for normal libraries. So now I'm going to explain the mechanism that we're now introducing into the JavaScript standard to help leverage the elements, the security elements of JavaScript that I just mentioned, in order to make it very pleasant to address the library issue. The Realms API proposal is a proposal before the committee. The Realms shim is a shim that we've jointly engineered with Salesforce. It's a shim of approximately of the proposal. Unlike most shims, it's not just trying to approximate the proposal, it's trying to provide real hardcore security right now, and Salesforce is already migrating this code base underneath a 5 million developer ecosystem that they have. So there's a new global object named Realm. It has a static method called make root realm. So when Alice in one realm says make root realm, at that point she is creating a new root realm. And a new root realm is a realm that has its own fresh set of primordials. So between Alice and Bob here, there's the same old identity discontinuity. But we're going to, so we have to deal with the identity discontinuity during the bootstrap. We're going to try to use the bootstrap to get beyond it. So when Alice says make root realm, she also gets, as a result, a instance of the realm object, the root realm, shown as the lowercase root realm object, that has a accessor property named global that points at the new realm's global, has an evaluate method for evaluating code in the scope of Bob's global. And the root realm object is Alice's object for manipulating the new realm, but the root realm object is itself an object in Alice's realm. And a difference between what the realm shim accomplishes and what the browser gives you with same origin iframes, or Node gives you with VM create context, is that this new root realm is born with no host objects that are implicitly granted. That it's up to Alice to populate Bob's global with those additional objects that Alice wants Bob to see. And anything that's not explicitly granted by Alice is completely absent from Bob's realm. So what this is doing is, let's go back to the analogy of a virtual machine monitor. All of the access to the host environment that JavaScript programs see is by lookup of names on the global object. So if Alice populates Bob's global object, then no matter what the underlying platform host is, Alice is acting as a virtual host for Bob. She can create for Bob, she can emulate any host environment she wants, or invent new ones. Bob also has a realm class in his primordials. And if Bob invokes realm.makeCompartment, a compartment is also a kind of realm, but it's unlike a root realm, it's incredibly lightweight. Bob's compartment shares almost all of the primordials of the root realm that created the compartment. That's the defining difference of a compartment. The only objects that need to be created that are visible that characterize the compartment is there's a object created as a member of the root of Bob's root realm, which is the object representing the Carol compartment. The Carol compartment has its own global, and it has its own function constructor and eval function that evaluates code in a scope that terminates in that compartment's global scope. And other than those objects, everything else comes from the root realm that compartment is created in. And then if Alice does a deep freeze on the Bob realm, and let me apologize for the name deep freeze, we will probably be renaming it to something less prone to misunderstanding. But what deep freeze does is it essentially freezes the primordials of the Bob root realm. It does not freeze all of the objects that are not part of the primordial graph, but it freezes all the primordials. And because of the property that I mentioned earlier, that there's no hidden state, the result, leaving aside the two exceptions of date and math random, the result is that the primordials that the Carol compartment is sharing has no mutable state left and has no access to the outside world that was not granted by Alice. And the result is that many compartments. The compartments are featherweight protection domains. Many compartments can be created within this context, and there's no identity discontinuity among them. An array created by one is instance of array as checked by the other. It's even the case that all of the different function constructors share the same function prototype. So even the different functions from these different compartments evaluating in the scope of different globals, they're still all past each other's instance of test. Oh, and the really important point here is that these things have no ungranted access to each other, since what they're sharing is only these transitively immutable objects. What they're implicitly sharing is these graphs are born fully isolated from each other. They can only interact or become further connected according to the decisions of the objects that have a foot in both, which initially are the objects that are in the position of having created them. So that topological constraint makes that the ideal position to stand to express the security policies by which these things interact. The realm's shim really rests on this particular very small, amazingly weird piece of code that brings together some of the worst elements of JavaScript, the sloppy mode, the with construct, direct eval, in order to create the mechanism for intercepting the global scope lookup. Basically, by doing a with on a proxy, any attempt by the source code to access a global variable, the source code is being evaluated there by direct eval. Any attempt by it to look up a global variable goes through the scope proxy, which is then able to intercept the scope lookup and thereby prevent access to the genuine global scope that was created by the underlying browser or node primitive. And by completely insulating all this mechanism from the genuine global, we can create environments that have the global of our own design. The entire kernel that we've built around this, that we went through a rather rigorous security review on, is less than 700 lines. Last I heard, there's actually only 4 lines of it that we have not been able to reach coverage-wise with our tests. And as I mentioned, Salesforce is already in the process of migrating a 5 million developer ecosystem on top of this mechanism. This mechanism is amazingly fast. We put a lot of engineering effort into the version of secure EcmaScript that we built Caja on. This is amazingly faster than Caja, the SES in Caja. There's something, we need to do more measurements, because right now from our measurements, not only have we not been able to measure any slowdown for the typical case compared to native. In the typical case, I should mention, there's an optimization that I didn't show for most global scope lookups that intercept it. And it's only the atypical case that actually has to go through the proxy. But for the typical case, not only have we not been able to measure a slowdown, it seems to be measuring at faster than native, but within the margin of error. So clearly we need to do more measurements.
So what are these numbers? What did you actually measure?
So these numbers are measurements from JF Paradis of Salesforce that I should also mention, these numbers were put together in a hurry to be able to report them by the last EcmaScript meeting. They're not, I don't know if more up-to-date numbers are done, but we're collaboration with JF, and we haven't heard of an attempt to revisit the measurement exercise. I can find out for you what was actually measured. I don't have that available immediately. There was a spreadsheet. There was a spreadsheet that JF shared with me that I think names the things that were measured.
I see. So you don't know if it's like a property access or function call or.
I can tell you the one place where we do know that there's a significant slowdown that does affect real code, and that is coping with the override mistake. The override mistake is that if you, I'll just talk it through with regard to the most egregious example. If you naively freeze object.prototype, then you've made the toString property, object.prototype.toString, into a non-configurable, non-writable data property. If other code then engages in the very normal coding pattern that much old code in fact engages in with no problem, of, let's say, defining a function, a constructor function using the pre-class pattern. They define a constructor function named point, let's say. It's an XY point. And then they want to initialize the prototype of point by saying point.prototype.toString equals some function, the toString function that they want to be the point override of the built-in toString function. That assignment will fail because of the spec mistake that we made in ES5 that I have been unable to convince the committee to correct, which is that creating a new property on an object that would override an inherited property that is non-writable, that throws, even though it's not mutating the non-writable property. So the workaround that that we do for that we have encountered as a genuine pain point, in particular that both Salesforce and Caja have encountered this. Not a pain point that's unlivable, but just something that that's unfortunate, is we replace those data properties with accessor properties, where the getter of the accessor returns what would have been the immutable data value, and the setter emulates what would have been the behavior if we had convinced the committee to repair the override mistake, meaning that if you tried to mutate it on the object itself, it still throws because the property is not mutable on the object itself. But if you try to mutate it on another object that inherits from that object, the setter notices that and emulates the assignment using defined property. The emulation of the assignment is not the bottleneck. It's not the pain point with regard to performance. The pain point with regard to performance is that reading the property now has to go through a getter. And for property, for in particular, object.prototype.toString, it's read sufficiently often, and the JITs are for whatever reason, not sufficiently aggressive at optimizing the code path going through the getter, that the difference between looking up the getter value versus looking up the property value is painful. And that pain is not reflected in these numbers. I will get you numbers that reflect that.
Okay. Thanks for that. I imagine there's also like more than toString, right? Like we're seeing like a lot more monkey patching of these primordials that I think you'd have to do a very similar thing. That's why I'm curious. I'm like even like what these units are. But like I guess like we could talk offline too.
So the monkey patching of the primordials that we're doing, oh, I'm sorry, I should also make clear, this is with regard to, this is not looking at the overhead of getting to the host objects through some intermediary layer, because there's nothing general about that to measure. It's on a case-by-case basis because it depends on what intermediation is desired. This is with regard to the sort of purely internal EcmaScript overhead of operating within this environment where your access to the global is virtualized through the mechanism that I showed, but with the optimization that I didn't show on that little piece of code.
Sure, but I guess you kind of can measure like the no-op policy, right?
The no-op policy would be direct access. You can, Alice is in a position to give direct access. If it's intermediated through, let's say, a function that's just a front-ending function that forwards everything to the underlying function, we could measure that. It shouldn't be any different than any other case of a forwarding function. So whatever the overhead is of going through an extra function. So there shouldn't be any mystery there, but yeah, we could measure that. And with regard to this also, we do know that there used to be a penalty for interacting with frozen objects, in particular in V8. Simply interacting with frozen objects for many different objects would put you on the slow path. That's been corrected across V8 and all engines. The override mistake issue still has a real penalty, but other than that, there's no penalty for interacting with frozen objects. So this is essentially the Realms shim API, the API that we're able to shim with hard security properties and a very, very small TCB, a very small trusted computing base, less than 700 lines of code now. And the constraint with regard to our security goals is that any parser that's introduced to the overall picture cannot be introduced for the sake of security. Because any parser is going to blow up the overall code size by a lot. Any user level parser written in JavaScript. So we want the security of our system not to depend on the parser. So this is a parser aside. This is what from Realms we can securely emulate with no rewriting. And to emulate module loader, that's part of the overall Realm API. It's not something we can securely do in a shim without rewriting because we don't currently have any way as in a general host independent JavaScript way to intercept loading behavior. Of course, for Node specifically, we have a place to stand where we can do that, but not obviously from the perspective of unprivileged code. But still, Node gives us a platform in which we can experiment with a deeper integration that does give us the module loading hooks that we need to deal with that securely. From this point on in the talk, I'm going to assume that we're somehow intervening with module loading. And the security story on that today is that we're using untrusted parsers and rewriters to like rollup and ESM to rewrite code expressed in terms of modules into code expressed more in terms of node modules with require and exports that then become strings that we can evaluate whose global scope lookup to require and export itself are ones we can intervene on.
Can I ask another question if it's okay?
Yeah, sure.
So with suppose we have more than just EcmaScript, and we actually have say buffers, or we have FS or something like that, that we'd like to expose to one of these realms. And within a realm, I call one of these functions, which will end up calling, say, in binding code, and the binding code will call my callback with an object. What happens?
So the answer, as far as the mechanism is concerned, is we've given you, this mechanism produces, it provides adequate material that whatever security policy you want with regard to that, we should, not for any security policy, but for many plausible security policies, we're trying to provide the mechanism that enables a large number of policies to be expressed with common mechanisms. So I went back to this slide here, where there's multiple coexisting compartments. It might be that one of these compartments was actually given the genuine FS module. And then it was code running in that compartment that had access to the genuine, fully dangerous FS module. That was then the compartment that ran the code for expressing the policy for attenuating the SF module into virtual FS modules that were then used to seed the other compartments. And by doing it in this way, you can give these other compartments differential access, and you can deny the FS module to those compartments that have no need for the FS module. This is actually the perfect segue to the rest of the talk, which is many libraries don't need the FS module. You would like a system in which you can evaluate the risk of linking in the library based on the fact that its manifest doesn't say that it needs the FS module, or if we and then link it in without providing the FS module, or for one that does need the FS module, you might have a policy about what attenuation of the FS module you want to provide. And a perfect example would be, what's the name in Unix? I forget the name already. For providing a directory subtree as if it's the entire file system.
You mean open add?
Change root.
Sorry, what's it called?
Change
To
root.
root.
Change root?
Yeah, CH root.
Okay, there's some other term that I was thinking of, but I'll just use that term. For example, the initial compartment given the full FS, first of all, doesn't even know that it's been given the full FS. The one it's been given could have already been attenuated in the same way. But if it wants to further attenuate it, in order to give another compartment access to something that goes through a file name remapping, in order to only make a subtree of the file system accessible as if it's the whole file system, that's clearly expressible. How easily it is to express depends, of course, on the specifics of your FS API, which was not designed to be attenuatable in this way.
Yeah, I guess so. So I totally buy this, and like we've done quite a bit of this. And oh, by the way, it's not Brian speaking; it's Dan, and I'm the annoying one. Sorry. You can, right? Like I totally buy that. I guess like what I'm worried about is FS. I have an attenuated version of FS that ultimately calls into real FS, which calls into binding code that creates an object that I then have to further. Like the mechanism described so far doesn't seem like it would help me with making sure that that's not the true object that I can't mess with.
I'm sorry, I did not. I thought I understood until you got to the conclusion. I realized I did not understand the question.
So there'll be an object created in the binding layer, let's say, yeah.
So let me back up so I can trace how the object got into this scenario.
Great.
Okay. Okay, so over here, I'm backing up all the way to this slide, where Alice is executing in the initial realm, and Alice is, basically represents the application that started with all of the authority of that process. And I've heard that there's some exploration in Node about trying to constrain the overall authority of the process or the overall authority of the application that finds itself initially running, and that's fine. Whatever that authority is, Alice here starts with all of that authority, and let's say that that authority includes the genuine FS object.
Mm-hmm.
Okay, now Alice makes a root realm here, and the root realm, let's say she does not give the root realm access to that FS object. And the reason she doesn't do it to the root realm is all the compartments created in the root realm share the root realm and share access to the global of the root realm. So going forward, so this is the no host objects. And in this case, Alice does not put the genuine FS object into this global. So over here, I showed the situation where the initial code that's run in the root realm creates this compartment named Carol. That's still code that Alice determined what that code is. So Alice can do this in a way that Alice gets a hold of the Carol realm object, and through the Carol realm object, the global of the new compartment Carol. And let's say Alice puts the genuine FS object on this global. And then or in either order, it doesn't matter whether Alice freezes Bob before or afterwards, because this new stuff is unfrozen by freezing the root realm. And then, starting from this picture, what Alice does is she loads all the rest, she makes all of the rest of her application following the bootstrap happen inside the Carol realm. And the reason she moves all the rest of her application logic into the Carol realm is so that there's no identity discontinuity between the pieces of the Alice application. So the only thing that remains to execute in the initial realm is the code that picks out the global authority, the dangerous global host objects, picks out which things should be loaded and what module loading policy to use to determine which module should get what, and then sets up the Carol situation so that everything else that gets loaded that's part of the application gets isolated and constrained by those policies, and all the rest of the application gets started from there. And let's say that each of these compartments now represents the a different loaded module of the Alice application started from that situation. And it was the loading policy that and the logic of that initial code executing in compartment Carol that further divided the FS authority. So so the Alice application, I'm going to say trusted. The trusted part of the Alice application, and now I'll be very specific what I mean by trusted, is the code of the Alice application that the Alice author decided that that it was okay for all of the Alice application to be vulnerable to. That vulnerability decision applied only to the code running in the Carol compartment. And that code used these mechanisms largely through parameterizing a module loader, but also by attenuating some of the dangerous host objects and deciding which module should get what, to hand out those permissions as described. Now, there is intermediation going on here. If Carol decides to give Dave a virtual FS that does this change root trick, with regard to piling up successive attenuations, it's successive attenuation. There is a trick in attenuation architecture that I didn't choose to explain in this talk, but I certainly can. That if you there's a way to express an attenuator so that chained attenuations of the same kind, like successive cheroots, can be basically the multiple levels can know about each other in order to collapse the successive attenuation into a single level of indirection. So you have to pay it one level of indirection, but if it's chained attenuations of the same kind, you don't have to pay multiple levels of indirection. You often don't have to. You can collapse them, and you can see the logic of how nested cheroots can be collapsed into the equivalent of one combined cheroot.
Yeah, I guess I had a simpler question, which is like I just like I guess walking through a concrete thing of like exposing read file, right? Like I'm not concerned about rewriting the path to be a virtual path or anything like that. I guess I'm more concerned that this function ultimately will be implemented in C++.
Okay.
That will be binding code that creates the objects that correspond to the buffer that you're giving me, and then
right. So one of the things that you have. So thank you. Now I understand the question better. Yeah, when Alice gives Carol the genuine FS object, that's a cross-realm object. There needs to be good support code pattern-wise for handling that initial cross-realm object with tweezers, because because even though I said it's up to the a user-level policy, when dealing with the genuine cross-realm object, because it leads to all sorts of dangerous things, we need to provide good conveniences so that naively written policies built on our conveniences don't accidentally leak access to the other realm and all of those strange C++ things. So that would wrap FS in a, we call it a facade, a front end that provides the same external API, but does it within this realm rather than within the original realm. Also let me, and the result is that the fact that the object in the original realm is backed by C++, that's dealt with. And I say this by experience. We had the same issue with all of the bizarre DOM objects in Caja, which we intermediated with very much the same kind of architecture. We put, but we created the library for intermediating with the DOM because that was a bizarrely hard thing to intermediate. In fact, it was where most of our security bugs were. But it was still a user-level library in the sense that it was built on SES. And then the users then, the normal users then never express policy with the underlying DOM node other than by handing it to our safe library for manipulating and virtualizing DOM access. I expect the same pattern to emerge on Node. Let me also pick up on another thing you said, which is from the experience with E, where we were bringing native file systems. treating them with the same kind of policy decomposition, is that one very common thing is that other modules don't need access to the file system. They need access to a particular file. And the natural thing there is to create an object that doesn't represent the file system. It just represents access to a file. And now access to the ability to read the file, or to put another way, read-only access to the file, or append-only access to the file, or revocable access to the file, then further becomes very easy to express attenuators. And we in fact found ourselves expressing all of those attenuators very simply in E, and I expect the same kind of leverage for wrapping the Node API with libraries of well-constructed attenuators.
So I would totally buy the E approach, having played with E myself too. If we burn things down, but I guess from experience with like node code into wild, I think there's a lot that we're putting in these policies. But like anyway, let me not diverge you more than I already have, and maybe tell us more about the libraries that you had in mind.
Okay, I mean, however bad the existing node APIs and practices of using them are by legacy node code, I mean, existing node code, it can't be as bad as the DOM situation and legacy browser code. I mean, the DOM API is properly blamed for being one of the worst APIs that human beings have ever designed. And nevertheless, we ultimately did succeed at creating a library for attenuating the DOM API that critical web properties then depended on. And Salesforce has now reconstructed a similar intervention of the DOM, reconstructed from scratch, but on similar ideas. That's also part of what they're building on top of the new realms. Okay, so going forward. Okay, so with those elements in mind, here's a key observation about existing libraries, which is a tremendous number of existing libraries are what we would call transformational, in the sense of what job it is that they're doing. They're libraries that are given inputs, compute for a while, and produce outputs, where the library itself has no need for access to I/O, it has no need for access to the user, it has no need for access to the network, it has no need for access to non-determinism or to be able to measure duration. Now, obviously, many other libraries do need those things, but there's an opportunity here with regard to the overall vetting burden and the issue of defense in depth. The principle of least authority is we can recognize that for a very large number of the libraries that we're using, the least authority that they need does not include access to the file system. It doesn't include, one very nice contrast is date arithmetic is transformational, but access to the current date is not. And you find that's reflected very much in the analogy we're making about what you can do in user mode versus system mode. A properly designed processor can't find out what the current time is. Computation, user mode computation can't find out what the current time is other than by making a system call, but it can do all the data arithmetic it likes. And one particular interesting observation is that for transformational libraries that are denied all of these things, including any source of non-determinism, they don't have adequate material from which to build something that they can use to measure duration. So there's this wonderful paper, Fantastic Timers and Where to Find Them, saying that even if you deny all of the explicit timers in the browser, there's plenty of implicit things you can use in order to measure duration, and then you can use those to read side channels, and that's like Meltdown Inspector, and a zillion other side channels that browsers have, and I suspect Node has as well. We can deny those transformational libraries that access. With regard to how to structure a module system such that it becomes pleasant to express which module can get what, there's both the module loading hooks, which are represented by other proposals before the committee that are rooted in the full realms proposal. And there's Mike Samuel's proposal for module keys, which are basically a very modular mechanism for modules to interact with each other, where they can whitelist which other modules they wish to grant things to, as well as whitelist which other modules they're willing to believe with regard to the veracity of what kind of information. The wonderful example is when you're forming safe HTML by appending strings that are allegedly HTML that were constructed in a safe manner, the one that's trying to, the module that's trying to construct the allegedly safe HTML needs to express a policy as to what other modules it considers to be ones that it trusts with regard to what strings are safe HTML, so that they can brand those strings appropriately. So these are all, once again, at the moment, they're all user level pattern issues. Mike Samuel has a shim for shimming the module keys thing, and which of these things should move into the platform and which of things should remain user level libraries is to be figured out as we go on. But the overall surface to present to the normal user, I think, is one in which this kind of per module distinction of authority and veracity is something we want to express. So in conclusion, I want to go philosophically large again. In conclusion, over the last few decades, civilization has made a transition where it now rests on the infrastructure that our industry has made. And Node is no small part of that story. It's a significant player with regard to that overall vulnerability of civilization to the infrastructure created by our industry. And the overall insecurity of the overall computational infrastructure really puts our civilization at risk. If you read realistic assessments of how much damage an all-out cyber war can do, it's really quite frightening. And as a security professional, I consider those usually to be underestimating the degree of damage. And the result, and my conclusion from that, once again, is defense in depth. We have to fight this on all fronts. And to the degree to which we can reduce risks at any level of abstraction, we can amplify the benefits that we can obtain safely at that level of abstraction. So let's clean up our mess. A bunch of references for some of the quotes in the talk and for other things that to be looked at. And then over here, let's see if I can actually follow this link and have it continue to project. Oops. It looks like I can't. So there's that link, which I will put in chat once I stop projecting. And that is to a challenge page in which we've created a sandbox, a playground rather, JS Fiddle-like playground where you can just type in code, and you're given what you're given in that playground are the things that transformational libraries would expect to have, but nothing else, except that you're also given a callback that we've seeded that environment with to a really egregious side channel. One that when you call it, it takes an amount of time that's really egregiously dependent on what the secret is that it doesn't want to reveal, such that if you have date.now enabled, notice the query string at the end of the URL, it's easy to read that side channel, and our demonstration code shows that. And our challenge is write any code that succeeds at reading that side channel when given only the things that would normally be given only to a transformational library. Okay, and now I'll take further questions and discussion.
Okay, I have another question. Thanks, by the way, for the whole talk.
You're welcome.
So your case of libraries and us deciding to not give somebody access to certain dangerous modules, right? So like I guess transformational libraries, like I totally buy. I mean, but like we can also just compile those to WASM and not do any of this. The thing that I'm curious about is when we actually set policies.
I'm sorry. When I was at Google most recently, I was in the WASM team. I know a lot about WASM. For a lot of these transformational libraries written in JavaScript, part of what makes them usable by other code written in JavaScript is that they're all within the view of one garbage collector. There's WASM right now is a flat address space, and any language compiled to WASM has to bring its own garbage collector into the WASM runtime. Dean and I made a proposal specifically to both WASM and EcmaScript for a weak reference abstraction to help with the garbage collection, well, to help with a number of things, but it was motivated for WASM by the garbage collection problem of garbage collecting cross-language between the WASM host language and the languages with their own garbage collector, including JavaScript compiled to WASM. And even with the best that we could realistically propose, we cannot collect cross-boundary cycles. And there's a lot of other problems. The WASM boundary does not appear transparent to JavaScript. You're not going to take JavaScript code, compile it to WASM, and use it from other JavaScript code that's unaware of that.
Sure, but okay, like I guess I think it's doable, but anyway, like I don't think that's not my actual question. So my question is when you were talking about policies, like it seems like really hard to do module policies that are not just like you get no access to this, because it's not like I depend on something, but that thing pulls in now 1,000 dependencies that one might log, one might do something else, one might phone home because that's what people do, and like we can argue that we should break some of that functionality, but I think it's really hard to set a policy that would apply like all the way down, as you're suggesting, if we're going to do a per module type enforcement.
So in building similar systems, that has not been our experience, but there is a genuine issue there that needs to be understood. That's certainly not obvious going in. There's the issue of where does the further subdivision of authority come from? So I want to distinguish between internal modules and external, and sibling modules. So when A depends on B, to A, B might just be one thing because it's represented by one thing they import, but B internally uses a whole bunch of other things that A is unaware of. So all of those other things coming along for the ride that, as far as A is concerned, are just internal parts of A. A should be in the position of, first of all, A only, I'm sorry, did I say A? Let me start over again. That's what I get for not using human names. Alice and Bob, not the same Alice and Bob that I was using. Module Alice is given a certain degree of authority, imports module Bob, and module Bob imports Carol through Joe as just internal mechanism within Bob. So Alice might already have given Bob limited authority, but that limited authority for this scenario has to, Bob's least authority includes all of the authority he needs to in turn pass on to his internal modules. Even if Bob as a module doesn't need a particular authority, if Bob has, as Carol as an internal component and Carol needs the authority, then Bob as a transitive component needs the authority. Bob's manifest should describe it, and Alice should provide something that at least appears to be that authority, is API compatible with the authority. Once again, Alice can still attenuate because as long as Bob can't tell or Bob is compatible with the attenuation. But Bob, in turn, basically at every level of composition, there's yet another TCB, there's yet another trusted computing base that's the component that obtains all of the authority that that composite is given, where the logic of that top level composite is the one that further subdivides as it loads yet other things.
So if we were building clean slate systems, I think we can do it. What I'm like afraid of is that I think like you end up requiring a lot more authority than we might think at first, right? Like take a wrapper around a database module, right? Like let's say a wrap around SQLite 3, which needs to write to disk. Whether or not this thing currently is running on behalf of Alice or Bob, let's say they're users, it might need one, to be able to write to one part of the database or another, or like, let's say file system, right? So like, I don't think, like if we were to make a per module policy decision, we'd be making the decision that you get to do whatever the hell you want. And I think like it becomes really hard to do anything but that.
Okay, so initially I expect that many people will do exactly that. And it very much reminds me of the original Android installation experience. Android upfront asked for all the permissions and provided no explanation of why it needed any one permission. And in any case, the normal user never would have paid any attention to that anyway. So what happened is users became habituated to just granting whatever the hell was asked for. And then developers became habituated to asking for anything. Then over time, in fact, actually partially inspired by some of the earlier work on capability-based user interfaces, that, admittedly distantly related, only distantly related to what I'm talking about today, but Android went to the new Android policy where, well, the part that's not analogous about the new Android policy is that for many permissions, it waits until it needs it before it asks for it. But the part that is analogous is that because of that restructuring of the interaction, when a user saw a request that seemed completely bizarre and unjustified by their sense of what they were doing, most users would grant it anyway, but some users would wonder, well, why do I need to give it that? It doesn't seem appropriate. And even a small number of users asking that question was enough to change behavior. So creating a mechanism, even if at first too much authority is granted habitually to too many things because it's the path of least resistance, and I do expect those kinds of failures will happen at first. You're still setting up a process that can be iterated. And are you familiar with Nassim Taleb, the author of Black Swan? He has this wonderful notion of the stubborn minority, where a stubborn minority who have a particular requirement, where the requirement is otherwise, meeting the requirement is otherwise not too costly by the producer, and meeting the requirement does not harm the other consumers who don't care about the requirement, that often the iterated interaction over time is that the producers satisfy the requirement of the stubborn minority. And the example is, look at how many foods are labeled halal or kosher. A tremendous number of foods are labeled halal or kosher, even though only a small minority of the people picking up those foods ever look for that label or care. Now, I want to come back to, though, the concession you made at the beginning, which is you buy it for transformational libraries. Well, if everything I'm talking about is only ever used for transformational libraries, the overall risk profile, the overall aggregate risk profile that we're faced through people building applications and giving attackers opportunities by linking in libraries that they should not have trusted, that risk profile goes down, the vetting burden goes down. It means that when you're trying to vet what libraries you should link in, you can see, oh, for these transformational libraries, I'm not giving them anything dangerous anyway. Maybe I still should worry some, but I can worry much less, and you can focus your vetting effort. And that, to me, is one of the main payoffs as a software developer, is our precious security review vetting effort can be more intelligently spent on the things that still are dangerous after we've been able to make many things that didn't need to be dangerous, making them undangerous.
Yeah, so I guess I buy that this works for transformational libraries. It still seems like quite a bit of mechanism that is doing security checks, and that's why the reason I brought up the WebAssembly is because the kind of work that you would be doing to get things to work is not security work so much as writing glue code that is probably not security critical. But like even so, like I guess that this removes some of.
I'm sorry, having participated in both, I can assure you that the mechanism that I'm talking about is much simpler than the mechanism needed to glue WebAssembly and JavaScript together.
Okay, I guess we'll agree to disagree there. But I guess there's like, how much of NPM is these transformational libraries?
So I've done a little bit of informal sampling, certainly nothing to quote statistics about, but I will say at least many. I believe, Bradley, are you on?
Bradley left.
Bradley had to leave.
Okay. Bradley told me that I can say that he says most.
I guess like actual data supporting that would be interesting, because like
I'm sorry. Bradley was, the most was a different question, which is NPM libraries that are compatible with an environment in which all the primordials are frozen, which is a completely different question. That's most. With regard to transformational libraries, we should just stick with the answer many, but it is many. I did a little bit of informal random sampling, and it really is many.
Okay, I'd be curious to see the data because we're seeing other things, but.
Anybody else have any questions? Any comments, criticisms, things they want to discuss? Okay, I will end the talk.
That's good. Thanks a lot. I will just quickly check if there is any question on GitHub, on YouTube. Give me just 1 minute for that, but I don't think there is any.
Okay.
Yeah, no question on YouTube. So thanks a lot for this amazing presentation. I think we will follow up on GitHub to see what the next step will be.
Okay, and where should I put the link to the challenge page that I promised?
You can put it in the GitHub issue that has been opened, which is on the security working group repo. I will pass the link of the GitHub issue in the chat right now. Here it is, and here it is on the YouTube chat.
I'm not connected through YouTube. I'm connected through Zoom.
Yeah, there is a Zoom chat. You can.
I don't know how to get to it.
So on the bottom there is a toolbar. Sorry, my Zoom is in French, so I have no idea what the name of the button in English.
Oh, show chat. Show chat.
Yes.
Okay, great. Thank you. I see the GitHub link. Wonderful.
Yeah. Thank you very much, everyone, for attending. Thanks a lot, Mark, for this great presentation. I will stop the YouTube live stream now.